There's a specific kind of frustration that comes with reading about the energy crisis these days. You see these incredible headlines, massive AI models, fusion reactors promising, infinite clean energy. But then you hit the fine print, you hit the bottleneck,
Hmm.
the hardware.
It always comes back to the hardware, and specifically how much power we just lose. Just moving electricity from point A to point B, it's the unsexy part of the equation, but it's the most important one.
Exactly. I was reading a report the other day about cooling costs for data centers training these new LLMs. It's astronomical. I mean, we are literally boiling lakes to teach computers how to talk.
Yeah.
And fusion, the amount of energy they waste just keeping the magnets cold enough to work is,
It's the whole reason we don't have fusion plants powering our cities.
right. Which is why the holy grail of physics has always been, and still is, the room temperature superconductor.
A wire with zero resistance, no heat loss.
No cooling needed, just pure efficiency.
It changes everything. I mean, overnight, if you have that, you don't just save money on your power bill. You change transportation, medicine, computing, all of it. But here's the problem. We've been hunting for this thing for over a century. We've thrown Nobel laureates billions of dollars at it. And the best we have are materials that, only work if you freeze them colder than deep space or crush them with the pressure of the Earth's core.
It feels like we're missing something fundamental, like we're trying to brute force a lock instead of just finding the key.
And that is exactly what we're covering today. We've got this fascinating paper by Jerry Z. Liu, Unified Theory of Low and High Temperature Superconductivity. And the mission for this deep dive is pretty exciting because Liu suggests we haven't just been failing to find the material. We've been misunderstanding the physics entirely.
That's a huge claim. So we're throwing out the standard textbook explanations.
We are. We're moving from a world of, particle collisions and cold physics to a world of structural geometry. It's a total shift in perspective. We're not looking at the actors anymore. We're looking at the stage they're standing on.
Okay, so before we get to the new theory, we have to understand the problem. Why do the current models fail? If I open a textbook, it tells me resistance is caused by electrons crashing into things.
Right, the Drude model. That's the standard pinball analogy. It's how we've thought about electricity since the early 1900s. So imagine a copper wire is a long hallway full of bumpers, the atoms. You shoot a pinball, the electron down the hall, it bounces. That bouncing, that loss of momentum, creates heat. And that's resistance.
Simple enough. So if I want less resistance, I just need fewer collisions, a clearer hallway.
That's the logic. But Liu points out this massive contradiction here, and once you see it, you really can't unsee it. Think about pressure. If I take that copper wire and I crush it under immense pressure, what am I doing to the atoms?
You're packing them closer together. You're adding more bumpers to the hallway, making it more crowded.
Exactly. So statistically, if the hallway is more crowded, you should hit more bumpers. Resistance should go up.
Right. If I try to run through a crowd, it's harder than running through an empty room.
But in reality, the exact opposite happens. For almost all materials, you increase pressure and resistivity goes down. And in some cases, you squeeze hard enough, resistance disappears completely. It becomes a superconductor.
So the model predicts A, and reality delivers Z. That's not a small mistake. That's a fundamental disconnect.
And it gets worse. Liu also takes on the whole sea of electrons idea that metals are held together by this liquid glue of free-floating electrons.
I remember that phrase, a lattice of positive ions in a sea of delocalized electrons. Sounds kind of poetic.
It does. But think about it mechanically for a second. If the glue holding a steel beam together is a liquid that moves freely, how does the beam hold its shape? I mean, you pull on a piece of metal, it resists. It has tensile strength. Liquid glue shouldn't do that.
That's a really good point. You can't build a bridge out of soup. If the electrons are just sloshing around, the atoms should just drift apart.
Precisely. So Liu says we need to scrap the collision model and the liquid glue model. Resistance isn't about crashing, it's about gaps. It's about the effort it takes to get from your home base to the highway.
Okay, let's unpack this new model. The paper calls it the electron tunnel.
Yes. This is the core idea. Imagine the atoms in a wire aren't just sitting there. If they're arranged just right and close enough, their electron clouds interact and they form a network, a continuous path that runs between the molecules. This is the tunnel.
So instead of a chaotic sea of electrons bouncing around, it's more like a dedicated subway system.
A subway system is a perfect analogy. Now here's the key part. In a normal conductor like copper, that subway system exists, but the entrance is inconvenient. The electrons live in their valence orbitals. Let's call that the street level. The subway platform is up a flight of stairs.
So to get on the train, I have to climb the stairs first.
Exactly. You have to spend energy to lift the electron from the street level up into the tunnel network. This is what Lou calls lifting energy, or SEI.
And that effort, that climb, is what we feel is resistance.
That's the whole idea. Resistance isn't the friction of the train moving. The train itself moves frictionlessly. Resistance is the energy cost of getting passengers onto the platform. But because of heat, vibration, they keep falling off the platform, and you have to pay to lift them up again. And again. And again.
So that constant lifting tax is electrical resistance.
Okay, so following that logic, what's a superconductor?
A superconductor is when you lower the platform. You lower the tunnel until it's flush with the street level.
Zero stairs.
Zero stairs. The lifting energy becomes zero. The valence orbital where the electrons live overlaps directly with the electron tunnel where they move. They can just drift onto the highway without any push. No energy loss.
That is remarkably intuitive. It turns a complex quantum problem into, what, a construction issue. We just need to lower the tunnel. Right. And this is where the theory gets really powerful, because it unifies the two things we know create superconductivity: pressure and temperature.
Okay, because right now, those two feel really different.
Yeah.
Squeezing a rock versus freezing it, they don't feel like they should do the same thing, but Lou is saying they're doing the same job mechanically.
Exactly the same job. Let's look at pressure first. In this tunnel model, the height of the tunnel, the distance to the platform, is just determined by how far apart the molecules are.
Okay, so closer molecules means a lower tunnel.
Yes. When you apply physical pressure, you are literally squashing the molecules together. You're physically reducing that distance. Squeeze hard enough, the tunnel lowers, it touches the electrons. Connection made. Superconductivity.
That makes sense for the high pressure experiments. We're just
Right.
forcing the connection. But what about cold? Why does putting something in liquid nitrogen lower the tunnel? You're not squeezing it with a machine.
You're not squeezing it from the outside, but you are letting it squeeze itself from the inside.
Explain that. How does cold equal squeezing?
Well, think about what heat is. It's vibration. It's excitation. When an atom is hot, its electrons are excited. They jump to higher, wider orbitals. The atom gets, puffier.
Like a person flailing their arms around on a crowded dance floor. They take up more space.
Exactly. And they push their neighbors away. There's high repulsion. But when you cool that atom down, the electrons calm down. They retreat to lower orbitals. They hug the nucleus tighter.
The person stops flailing and just stands still.
And suddenly there's less repulsion. The atoms can just snuggle up closer to each other just based on their natural attraction or even atmospheric pressure.
So cold acts like a chemical vice. It stops the atoms from pushing each other apart and lets them settle into that closed zone where the tunnels connect.
Spot on. Both pressure and cold have the exact same goal: reduce the space between molecules so the tunnel network connects. And this leads to a very specific concept in the paper called the compression bond.
The compression bond. This sounded important. Is this different from a normal chemical bond, like covalent or ionic?
It is. The source uses helium to explain it. You know helium is a noble gas, right? It hates bonding. It's a total loner. Even if you cool it to absolute zero, it won't freeze solid. It becomes a superfluid.
It stays liquid because the atoms just don't want to stick together.
Right. But if you apply pressure to that cold helium, it will turn solid. Why? Because you force the electron clouds to distort, to interact, and this forced interaction creates a new kind of attraction, the compression bond.
So you're basically bullying the atoms into bonding.
In a way, yeah. And Lou argues this specific bond is what you need to create the highway structure, the electron tunnel. Without that compression, you just have cold atoms but no connected path. You need that distortion to bridge the gap.
This explains so much, but I want to test this theory against the magic stuff. Because superconductors do things that feel like magic. Levitation, the Meissner effect.
Ah, yes. The floating magnets. The classic demo.
Yeah, and if I look at a standard explanation, it just says a superconductor expels magnetic fields. It pushes them out. But does this really say how? Does the tunnel theory explain the mechanics of it?
It does, and it frames it through something called the Lorentz force.
Which is what again?
The Lorentz force is a basic rule of electromagnetism. If you have a moving electric charge and you put it near a magnet, the charge gets pushed sideways.
Okay, standard physics, got it.
Now, in our superconductor, remember, the electrons are already in the tunnels. They're free to move with zero resistance. So when you bring a magnet close, that magnetic field hits those free electrons.
And the Lorentz force gives them a shove.
A massive shove. And because there's no resistance, that shove creates a perfect swirling loop of current on the surface of the material. That current generates its own magnetic field that is exactly equal and opposite to the one you applied.
It creates a mirror image.
A magnetic mirror. And that opposing force is what physically lifts the magnet into the air. It's not magic, it's a frictionless reaction. The magnet is floating on a cushion of electrons that are mirroring its every move.
But there's a limit, right? I've seen videos where if the magnet is too strong, the levitation breaks and the magnet just falls.
Yes. And the visual the paper gives for this is fantastic. It calls it the squash lantern effect.
I love that image, what's being squashed.
The electron orbitals. If the magnetic field is too intense, the Lorentz force becomes so violent that it physically distorts the shape of the orbitals. It flattens them like stepping on a paper lantern.
And if they get flattened?
They withdraw from the tunnel, the connection breaks, the bridge falls down, and the material instantly stops being a superconductor.
The magnet falls.
That makes perfect mechanical sense. You push the electrons so hard they fall off the highway. Now, speaking of pushing hard, what about power? The other big limit for superconductors is how much current they can carry.
The critical current density. This is huge for fusion reactors, right? You need these massive currents to hold the plasma.
Absolutely. And usually we think colder is better. We keep things super, super cold to make sure they work.
Right.
But this theory connects critical current to something totally unexpected. Black body radiation.
Wait, like the glow from a hot toaster element or a star?
The very same. The math gets a bit heavy, but the big takeaway is that the maximum current a material can handle is proportional to temperature to the fourth power, T4 to dollars. It links to the Stefan-Boltzmann law.
Temperature to the fourth power. Wait, that implies that a higher temperature allows for more current.
Exactly. It's a paradox. While low temperatures make it easier to get into the superconducting state, higher temperatures, if you can maintain that state, allow for much greater power throughput.
So a room temperature superconductor wouldn't just be convenient, it would actually be more powerful.
Significantly more powerful. For the power grid, for fusion tokamaks, a stable high-temperature superconductor is exponentially better than a low-temperature one. It can just carry more load.
Okay, I'm sold on the theory. It explains the resistance, the pressure, the levitation, the current limits. It even explains that weird flux quantization experiment with the donut shapes, which I understand confirms the current flows in two ways, with the electron and the hole it leaves behind.
Correct. The double flow prediction. It was one of those experiments that never quite fit the old models, but it fits this one perfectly.
So the trillion-dollar question. How do we build it? We can't carry around diamond anvils to create pressure. How do we get this effect at room temperature and normal pressure?
We stop using brute force pressure and we start using chemical pressure.
Chemical pressure, so tricking the atoms into squeezing themselves.
Precisely. The master variable here is resisting distance. We need dollars to be zero. The paper actually outlines a design philosophy for creating molecules that naturally pull themselves tight enough to close that gap.
So it's like matchmaking for atoms. What are the rules?
There are three main principles. First, leverage attraction. You have to engineer the molecule so the internal forces, like van der Waals forces, pull the structure inward. You want a molecule that's trying to hug itself tight.
Okay. Principle 2.
Electronegativity balance. This is the Goldilocks zone. Electronegativity is how greedy an atom is for electrons.
If it's too greedy.
It holds the electrons hostage, it pulls them too deep into the atom, and they can't get out to join the tunnel. But if it's too weak, it can't form the bonds you need for the tunnel structure in the first place. You need elements right in the middle, strong enough to bond, weak enough to share.
And the third principle.
Asymmetry.
That one surprises me. I would have thought perfect symmetry, like a crystal, would be better for a smooth flow.
You'd think so. But remember, we need compression. The theory suggests mixing large and small atoms. Imagine packing a box with just basketballs. There's a lot of empty space, right?
Yeah, you can see right through the gaps.
Now imagine you throw baseballs into those gaps. They'd pull the whole structure tighter. A small atom sitting between large ones can pull its neighbors in, creating these local zones of high compression.
It acts like a little clamp.
Exactly. This asymmetry creates the internal chemical pressure we need to lower the tunnel height without a giant machine.
So we're not looking for a magic rock. We're looking for a synthetic architecture.
It's a construction project. We're building a highway at the atomic scale using chemistry as our bricks and mortar.
There's one last thing in this paper that I found absolutely mind-bending, a hypothesis about where we might find these things in nature right now. Because we always think of them as these rare man-made oddities.
The planetary hypothesis. This is where Lou connects the micro to the macro.
Tell us about that.
Well, if pressure creates superconductivity, then superconductivity should be a very common state of matter in the universe, just not on the surface of Earth, but deep inside large planets.
The pressure is immense.
Billions of times atmospheric pressure. Lou suggests that the cores of large planets, Jupiter, Saturn, maybe even Earth, are likely massive superconductors.
Okay. And if that's true, what does that mean?
Think about the Earth's magnetic field. It protects us from solar radiation. It makes life possible. But we still debate how it's actually generated.
The textbook says it's moving molten iron.
The dynamo theory, yeah.
Yeah.
But Lou suggests it might just be a persistent superconducting current. If you have a massive superconducting loop inside the Earth, once a current starts, maybe induced by the solar wind eons ago, it never stops.
Because there's zero resistance.
It just flows forever, generating a magnetic shield that lasts for billions of years.
It gives me chills. We could be walking around on the crust of a giant superconducting generator.
It's a beautiful thought, isn't it? The same geometric rules that decide how two hydrogen atoms bond in a lab might be responsible for the magnetic shield of our entire planet. It implies superconductivity isn't an anomaly at all. It's a fundamental state of the universe.
It really changes how you look at the world. So if you had to sum this all up for the listener, what's the big takeaway?
The takeaway is that we need to stop being so afraid of the complexity of particles. The solution might not be in some new particle or a new dimension. It's about spacing. It's about the gaps.
It's not magic. It's just getting close enough to touch.
Exactly.